Hey, what's up? It's time to learn about linked lists. We're going to focus on a singly linked list in this tutorial. This is something to get you started. This is something you should memorize. If you spend any time thinking about these edge cases, you're not going to finish the code challenge in time. All right. So I've been doing some code challenges and I'm realizing that you have to be really efficient. So one of my goals is to memorize and sort of optimize the code that I'm writing so that I can do better in these code interviews and actually work on the real algorithm rather than the supporting data structures. Hey, I'm Paul Solt from Super Easy Apps, and I'm glad that you're here learning about algorithms. We're going to dive right into the code in Swift, and we're going to learn how to do this. I've got an Xcode project that we can play around with. So let's jump on over to code. We're learning about linked lists, and we're going to do a single linked list in this, and this is all going to be in Swift. All right, so let's focus on what we're going to be covering. The big thing for this is we're going to touch on optionals. We're going to touch on generics. We're also covering equality or equatability and output. So debug output. This is just going to be a basic implementation of a linked list. We're not going to cover all of the edge cases, but this will be enough to get you started. We're going to have some rules on what needs to be implemented, and then we're just going to sort of go ahead and do it. So let's start off and talk about what a linked list is. And I think it's helpful to see a diagram. So let's draw a diagram. I'm going to draw all the diagrams in yellow. And in Swift, we have the ability to do optionality so that we can point something to nil, like we could in Objective-C or C++ or Java. And here, we're just going to use some values. So let's go 3, 5, 7. And then we're going to have a concept of what's called a head, which is going to be the head pointer or the start of the collection. The other thing that we're going to want is a tail. And this is important when we're appending things, when we want to add things to this. Knowing where the end of the linked list is super helpful. We don't have instant access like an array. So if we were to look at an array, arrays are different in that they're a continuous block of memory. We call that a contiguous block of memory. And they have indices that are going to start zero base. And let's see if I can get this like me. So we're going to have 0. And this is an array of size 6. So I can just say, give me the first element, and it's going to be right here. For a linked list, I can say, give me the first element, and it's going to be right here. But if you want the second element, I have to go to the first element, and then I have to follow the pointer to get to the next one. And if you want the third element, then I have to follow the pointer here. So that's 1, 2, 3 operations. Versus an array, if you want the third one, we just go here, and now we have the data, which might be like 12. Okay, so linked lists are beneficial when you want to add stuff to the end here. So we want to make a function that can append, and we want to make a function that can delete. So if I want to be able to remove something, I want to be able to delete. And so that's the gist of this, understanding how the edge cases work, what to think about, being able to write this in as tight code as possible and then memorize it so that you can use it in code challenges without having to waste time is really important. If you waste any time trying to think about, oh, what is the edge case here? Oh, I don't remember. You're not going to have enough time. And if you're trying to do some debug printing and you get stuck with the optionals or the generics get in the way, you're going to waste precious time that you don't have to waste. And then if you're having cycles or something and you need to check equality, then you need to understand how to write your equatable from scratch without having access to the compiler. So that's what we're going to focus on in this. I hope that this is helpful, and let's dive in. As we implement some of the algorithms that we're going to do the delete and the append. I'll come back to the whiteboard and explain them, but to start off, let's just start with stubbing out. So we're going to stub out code, and we're going to do that just so that our unit tests pass. Not pass, our unit tests build. We're not worried about making them pass yet. And then we're going to implement each function one at a time. So we're going to need to be able to count. We're going to have to store some additional stuff. So that is linked lists. Let's go ahead and get started. We're in Xcode and we've got our notes on the right. So let's see what's going on here. I've got a Swift package. We're just working on a single code file. I've got the set of instructions here, and then we've got our unit tests that are not going to pass right now if we try and build them. So our goal is to go through this and try and complete it. Now, this is the starter copy, so I'm going to have a begin version of this. This is going to be the solution, and we're just going to walk through how to do this. So we're implementing a linked list using generics. We're going to be storing optional types for items, which could be ints or strings that we could pass in using generics. We're going to keep track of the count because this is really useful in a lot of the code challenges to be able to insert a specific index or to count the number of nodes and do stuff like that in constant time. So just keeping track of it's going to allow you to do that. And then we're going to implement two methods, append and delete. Now I'm optimizing everything for speed. So we're going to skip the parameter names using the underscore variable here. Append's going to be constant time. So we need a tail in order to make that happen. And then delete's going to have to be a linear search, trying to find the node and then remove it if we find it. We're going to verify that this code passes the unit tests that are written that will cover a large portion of these two operations. And so let's dive into getting started. So we talked about stubbing out the code. That's going to be the first thing that we do. And I'm just going to go ahead and get started with that. We need two classes here. And let me get in the code window. Okay, I'm going to go into insert mode. I'm in Vim mode, so I'm going to do some keys. And I do have keyboard shortcuts showing up on the screen so you can sort of see what I'm typing. So we're going to create a node. It's going to be an item using generics. And then we're going to have a class linked list item using generics. And we're just going to go ahead and build. That should build. If we try and run the unit test with Command U, we're going to see a lot of failures. So we have no append, we have no head, we have no count, we have no delete. So there's a lot of things that we've got to stub out in order to make this work. So let's go back over here, because that was a lot, and let's stub out our node class. So we're going to have an item. That's going to be of the generic type, and then we're going to have our next, which is going to be another node of type item, and that's going to initially just be nil. So we don't need to do much there. Actually, I don't know if we need to be as specific, but I think being specific is fine. So we're going to have our init, again, trying to make this as tight as possible and avoid as much extra typing as we can. I'm not going to set the next pointer here just to save on typing. And then that will stub us out for now. Next up, we're going to do our linked list. So a linked list, we talked about having these head and tail. So let's go ahead and set that up. This is going to be a node of type item. I'm going to initialize this to 0. So these two will default to being nil. That way we don't need an initializer and we can focus on just our functions. Then we're going to have a delete. And we're going to do it based on node because that's going to be beneficial in some of the code challenges. So I'm just going to set it up so that we're set up for success. And I forgot the parameter name. So let's go ahead and do that. Okay, apparently I'm calling description directly in this unit test. I'm just going to remove that. And I'll fix that in the other one. And then what is this? All right, so we're not yet equatable. That's fine. We're not going to pass everything. That's also fine. So equatable is next. So we've sort of stubbed out the gist. Okay, so let's work on equatability, and then we'll work on being able to print these so that we can sort of see what's going on here. So to start, let's go with equatability. Okay, if we do this, it's going to give us we need to give it the conformance. Now you're not going to have autocomplete, so you're going to need to know how to type this from scratch. So that's going to be static function equal, and then left-hand side node, right-hand side node, and then the return type has to be a bool. What I'm going to do just to keep this simple is just compare the objects to see if they are the same identity, which is basically comparing pointers. This is a potential pitfall where you might get stack frame issues. So just make sure that if you're comparing the actual pointers, you're using the triple equal sign, not equal. If you're comparing the actual item value, that's a little bit different. But that's going to be our starting point. So that'll cover us. Now for making this printable, we're going to do the custom string convertible, and just remember, like, if you want to do this, you have to remember that string, and then you have to write the var description without any kind of autocomplete. And we just need to return a value here. So what we need to do is, this is a node, so we just want to print our value, and then if we have another node in the list, we're going to print an arrow, and then we're going to print the next node. And it's going to be recursive, so it'll just keep going until we get to the end. If we get to the end, we just print out the item value, and in this case, that would be probably nil. So let's do that. I'm going to use, I think the tightest way to do this is a guardlet to do that base case. So we'll say next is equal to, or is just that. So we're going to unwrap the next if it exists. And then if it doesn't exist, then all we do is we return the item's value. This makes it so that we don't have optionals on the next line. So then I can just say return. And then we're going to do string interpolation here. And then we're going to go to our next node. And so we're going to call the nodes, it's going to be next here. It's unwrapped, so it's not optional, so we don't have to deal with that. We've got our arrow, and that's just going to keep sort of going until we find the root or the end, which is our tail. And then we are going to stop and print out this value. Okay, so that's printing. I'm going to cover the same case over here. And this is just in case you get stuck. Like, this is something that you could do at the very end if you're totally comfortable with it. But if you're just starting this for the first time, write it so that you can play around with the linked list. And then when you're actually doing it, this is something that you can skip if you remember exactly how to make a linked list and you don't have any problems, so that you can print it out. So here, the easiest thing to get started is don't do a return statement. Just start writing the thing, write it as a single line of code. And in this case, I like to print out the head. So I'm going to do head.item, and then I'm going to do comma, tail, just to sort of see what are these values. This is helpful for debugging if you need to do it. Next, I'm going to do a new line, indent it with a tab, /n/t. And then what I want to do is I'm going to print out the variable name head and then an arrow pointing to the first thing. And then the first thing is just the head, which is now a node. And so then it should do our node print statement. Now, if you care about speed, like this is all you need to do. The problem is this is not as easy to read and you'll see warnings. So if the thing is showing you warnings, that's going to make it a little bit funky. But this should allow us to sort of see, okay, what are things looking like? And then if there's any kind of print statements, we already get output that's formatted. Okay, but there are potential problems, and I'll show you how to, we can clean this up. With the nil coalescing operator and the any, but I'm not going to do that right now. Okay, so we've stubbed out everything. We've got it building, which is great. We've conformed to the two protocols that we needed. And then our next step is probably going to be to write the append. We've got our node, we've got items, we have a next pointer, we have a head, we have a tail, and we have a count for our data structures. And so you can sort of see this is what we're trying to build. And just to go over, the search for finding something in this list is going to be a big O of n. Deleting would be big O of n, unless it's from either the head or the tail. Then it would be big O of 1 because it's constant time. Appending is big O of 1. Inserting at index, you're going to have to find the index and then insert, so it's not like an array. So it's going to be big O of n. And then prepend would be big O of 1. So the real benefit is append and prepend, but that also breaks down if you're doing like large amounts of operations where you're going to have to dynamically allocate and free memory. In some of those situations, a array is actually better. But regardless, we're talking about linked lists, and we need to learn how to add nodes and think about that, and then we'll get into delete. So let's talk about append. There's really two edge cases that we're going to need to handle here. There is the case where it's our very first element, and then there's the case for sort of everything else. And then we've got a little bit of bookkeeping. So let's go over what this would look like. All right, so our base case is going to be empty. And then once we have that, I am... let's go through this. So if we have an empty one, we're just going to have nil. And then we're going to have head. Head is going to point to nil. And tail is going to point to nil. I want to give myself a little bit more room. So let's move this over. Just say nil is here. And then we're going to have head and tail. So this is empty. we've got a variable for our count, and that is going to be set to 0. So I'm going to try and annotate it this way. If we want to append something, then we have to go ahead and we have to create a node. So what is that going to look like? Let me just redraw the next stage. So that's our base case. And then we'll just go ahead and we'll create a node. And let's append. Let's go with 4. So we're going to create a node 4. A new node 4 should point to nil for its next pointer. And now we have to associate with head and tail. So all we're going to do is we're going to point both head and tail to this. So that's just going to look like head points to here, and tail points to here. So that's really it. And then we're going to have to increment count. So if we're doing this, count is now that. So initially, head was nil as well as tail. And then when we go in append, we create a new node that has a next pointer that's nil. And then all we have to do is set head and tail to point to this. So that's our base case. And then if we go back, let's switch colors. So what if this is not empty? Let's start with a couple more nodes. So we'll just start with 2 nodes. And in this situation, we're going to have our head. We're going to have our tail. And let's have a node here. So we have 4. And let's say we have 12. And what do we want to do? We want to append 6. Okay, so let's just redraw. It might be easier to follow along if I redraw these. So let's try that out. Let me think about this. So that one, sure. Okay, rather than redraw, let me just copy. And now what we're going to want to do is we're going to make some changes. So we're going to create a new node. I'll do this one in red just so that you can see the transformation. And that new node is going to be, I'm just going to put it down here. We're appending 6, so we're creating a new node. 6 has to point to nil. This is important. When we insert, we don't want to create a cycle by accident by like reinserting a node that was at the beginning, but we'll talk more about that. So we want to make sure we clear that pointer, and we're going to have to update this reference. So if I annotate this a little bit more, this is our next pointer. So we're going to be adding or modifying our next pointer here. And then this is going away. And then the other thing that we want to do is we want to point tail down here. And this is going to go away. And so we're always appending. We're always adding to the end. And we're always setting tail to whatever is last. And then tail is always pointing to nil. And then if we're keeping track of our bookkeeping, the other thing that we're going to try and do is keep track of the count. So this is going to initially start at 2. And then when we go in and make this change, it then becomes 3. So that's one thing that we need to do. So what are the common things that we're doing here? Well, every time we start, we're going to have a edge case if it's empty. When it's empty, we're going to need to update head. And every time we're adding, whether it's empty or not empty, we're always going to be adjusting tail. So tail's always going to point to the new element that we're adding. So 4 was the new element we added up top, and then 6 is the new element that we added down below. And so we're always going to update that. We're always going to update our count as well. So that's going to give us some idea of how to structure this in code. So let's go ahead and code this up now that we can see this visually. I think drawing it out or like copying it makes a little bit more sense than if I just mark up the original, because then you can't see what the original is. And then it makes me hard to annotate if there's any questions. Okay. We're jumping back over to Xcode. And I know I stubbed this out. I put append below delete. I'm just going to shift it up with Command Option and then square bracket. And give myself some space. Okay, so I got Vim mode on, and I'm going to be going through this. So let's type out some code. In this case, let's just think about our base cases that we talked about. So that's going to be our first step. And we're just going to say if head is equal to nil, we'll do something. Otherwise, we'll do something else. So this is depending on the tail. This is our initial state or base case. And then anytime we append, no matter what, there's a couple things that we want to do. One of them is we've always got to point the tail to that new node. So we talked about that briefly, but this is the new node, tail needs to point to it. And here's the new node, tail needs to point to it as well. Maybe I should have drawn that one in red so that it was clear that that was the new node. But I think you get the idea. So we can just annotate that real quick and just create it there. Okay. So let's do that. We're just going to say whatever this node is, because we're passing the node in, we're going to say tail is equal to this new node. And then we're going to say count plus equals 1. Okay, so for our initial state, if head is nil, then all we're going to do is we're going to say head is equal to node. That's our initial state. And then appending, this is maybe the most complicated part of this, but it's not complicated. We're just going to ask the tail for its next value and set it to node. So we're creating that relationship that is, we are going from this state to this state. So we're just saying 12, your next pointer is now going to be 6. Okay. Then the next thing that we want to do is there's a potential cycle. This is a potential pitfall. So you're going to want to make sure you clear out the node. And this really becomes apparent if you delete and then append the same node. You can create a cycle. So make sure to clear state when inserting. Unless you want to merge lists, then that might be a case where you'd want something like that. Okay, and that should be our append. Let's go ahead and run the unit tests and see how well we do. All right, so we don't have anything with delete working yet. That's fine. And we can see what the print statements are. So when you're working on this, being able to see print statements is super helpful. So before we were just seeing nils,
now we can see that we have optionals. Now this is where you might want to customize the string output. And so we can fix this so that it's a little bit easier to read. We're going to jump back over to linked list. And down at the bottom, we have this description. So I had to clean up here about using the nil coalescing operator and the any. This one's non-obvious, and I just found out about it yesterday. So I've been looking for a shorthand way of doing this, and I didn't really have a good solution except to create temporary variables, and I didn't really like that. So if you were just to write this, it's going to tell you that it can't convert string to expected argument of type item. And I want this to work. And so one of the ways we can do that is we can say, well, treat nil as any, and then the type system won't complain about that. And we can do the same thing here. And this is really just for debug output. Like all I want is simple output that's easier to read. And once you start doing collection types, it becomes really hard to see what's going on. So this is just something you can memorize, like if you're struggling, and you really only need the description if your like tests are failing and you're not understanding like why, and you want to debug and you want to see like cleaner output. This can help you, but if you're in a pinch, this is going to take more time. So keep that in mind, like how much time you have. If you can just crank it out, great. If not, punt it to the end when you have a little bit more time to catch up on things. All right, so I don't even know what my tests are off the top of my head, but just seeing the output looks a lot nicer, not having all those optionals in the strings. So that's my first recommendation. And now let's talk about deleting. Okay, we're back and we're going to be talking about delete. So let's jump back to my notes and get started with that. Okay, I'm going to make that full screen so that you can see what I'm doing. Let's see, do we have space here? I'm going to go to a new page. No, let's see if we can fit it. Let's see if we can fit it. I'm going to just put it over here. I don't know why I called it 3 delete, because this is just delete. Okay, so we've got some things to think about. And this is a little bit more challenging. Let's see this example over on the left. This is a little bit more challenging with a singly linked list, because if I want to remove an element, let's say it's in the center, I need to go to the element that's before it and ask it, okay, head, find me the value that's storing 1 that points to 2. And then we can adjust the pointer and we can change the pointer from this next to point to 3. So 1 can point to 3. We do have edge cases when it's the head. Like if it's the head node, we're going to need to have some special logic to update the head value. And the same is true for the tail. If we're updating the tail and we're trying to delete the value that ends up being at the tail, not necessarily intentionally, but like it could be if we're doing a stack or a queue, we could be popping or one of the values from the front or the back. But in this case, the tail needs to know about the previous. And so we need some bookkeeping to keep track of a previous. So that complicates the algorithm. And initially I had an approach and it sort of worked, but it didn't work for one of the base cases. And then I was like, something's wrong here. I'm not iterating through properly in Swift. And so I went back to the drawing board, created some new unit tests, and then got it to pass by updating the logic. So what we need to do in order to delete is we're looking for a node to delete, and we're going to search until we find it, but we're going to have to keep track of the current as well as the previous, because that's going to help us with the bookkeeping at the end. And we only want to adjust the counts when we're actually removing a node. So there could be the case, and this is one of the other edge cases I didn't think about. There could be a case where we try to delete a node that doesn't exist, and we don't want to subtract our counts if we actually didn't delete that node. So there's a lot of edge cases to think about. In a In a code challenge, you might not need to think about all of these, but just being aware of them, I think, is super helpful. And it just sort of sets the frame of mind. So how do we create an algorithm that can sort of iterate through and remove stuff? Let's go ahead and copy this. I got that extra line. Awesome. Okay, which value do we want to delete? Let's try and delete. Whoops, we missed our top of our T. So if I want to delete, let's say 2, what are all the steps? What are all the steps that I need in order to do that? So this is the node we want to delete. How do we find it? So we're going to need to have some bookkeeping. We're keeping track of our count. Count is going to be 3 in this case. And we're going to have to walk through the list. And that is probably the one thing that's been tripping me up a lot. Just thinking again in terms of linked lists and like iterating through things, because this is not how I normally think, because I haven't done problems like this in a long time. So what we're going to do is we're going to create a temporary variable called current. And current is just going to keep going through the array. Or sorry, not the array, the linked list. And we're just going to keep updating. So initially it's going to start at head, but we also need to have a previous. And previous has to be one step behind current. So previous has to point to nil initially. So it's probably easiest for you when you're doing these challenges to just have a variable view over on the right. And so previous is going to be nil, and this is something that we can update. And then current is going to be head, which is going to be 1. So we're just pointing to whatever the value is. And we're going to iterate and try and delete node 2. So we need to keep moving until current is equal to the node that we want to remove. So the node that we want to remove has the value of 2. We need to do some kind of equality here. And so we already have that sort of set up to just look at the actual objects, because we've got objects in this linked list. So that's going to be okay. So while, what's our end condition? So we want to have some kind of while loop. So while I'm going to do something with current dot next is not equal to the node or something like that, or while there still is a node. So in this case, we can think in terms of Swift, but we're going to be iterating through. So something like this, and then we just would say previous at the top is equal to current. And then you do some work in here. And then you're going to say current. And we're going to define current and previous outside of the while loop. So that's going to give us references so that at the end we can use our previous, because we talked about needing access to previous to update tail. All right, so that's kind of like pseudocode, thinking about this. So let's just draw out, like if we actually go ahead and were to make some of these changes, what does that look like? So let's say we found value 2, so we want to get rid of value 2. We're going to have to update our next pointer to now point here. And head and tail don't need to be updated. So those are okay. Those are still pointing to the correct values. So then the end result, what we get is just going to be sort of the smushing together of these values. So you're going to get 1 points to 3, which points to nil. And then your head and your tail are still pretty much same exact thing, just a new drawing. Okay, so that's what we're going to end up with. The only edge cases that we need to be mindful of, I'll just put them here, is head removal, and I'll call this bookkeeping. And then tail removal. And that's why we're using the previous. So previous is really important over here for keeping track of that. That's the gist. We're walking through this until there's no more values. Now I'm gonna write this in a Swift optional way, which is going to be a little bit different than what I have here in the pseudocode, but I think it's going to make a lot more sense once you start to understand that. And so let's go ahead and see if we can implement this. Oh, and the last thing I would say is don't forget the we need to do the count. Okay, so if we remove it, we want to subtract the count. If it's not actually in there, that's another edge case. So there's a lot of edge cases with deleting. Not every challenge is going to require this, but if you do need to do it, you just have to think through it. And this is where linked lists that are singular in that they only have next pointers require a little bit more work when iterating through, but this is a good skill to practice because it's helpful for other types of code challenges. So let's start defining our variables. I am going to say var current is equal to head. That's our base case. We talked about having a previous. This is going to be set to nil. And so if I'm setting to nil, I actually have to do the whole type specification. Otherwise, it's going to complain about it. And then we're going to loop through until the node is found or end of list. I'm going to do a while let here, and this is going to simplify some of the syntax. This is something that you have to practice to understand and have to like walk through to understand what it's doing. So essentially this is like an if let, except it's going to keep on looping as long as there's another node, and it just assigns it to next. It's unwrapped so we have full access to it without having to dance a lot with more optionals. So next I talked about having previous equals current. So this is where we're setting that. And then at the end, we're going to do current is equal to next. And then in here, what we want to do is we want to check equality and delete and break out. There's a few things. Delete and decrement and break out. So there's a few things that we need to do in here. At the very end of delete, we're going to have to do some bookkeeping for head and tail. Okay, so that's the overall structure. How do we check for equality? So assuming you have the equatable set up, you can just say if node is equal to next, then we're going to delete the node. And what does that look like? We're going to say current dot. Now here we have to use current because current is the only thing that has a reference that we can update. We can't use next here. Next is a let. So writing to next is not going to help us. We have to be on the previous node. So I talked about having the previous node right here that's head value 1. In order to remove head value 2, or sorry, value 2, we have to have the next pointer here. Okay. And once we do that, we just say this is next.next. So this is where like super nice not to write current question mark dot next question mark dot next, or whatever we'd have to do if this was totally optional. All right, so that's going to actually delete the node. It's just going to say, okay, skip over you, give me the thing that you're pointing to, which in this case is 3. So 1 is now going to be pointing to 3, and we're good to go. Next, we have to actually do our decrement. So count minus equals 1. We've removed a node. So this is a case where we removed it. We don't want to keep going because we're just going to remove the first instance. That's something that you could clarify depending on the scenario that you're trying to do. Like how many instances are you removing? All instances? Well, if you're removing all instances, don't break out. Just keep removing matches. But in this case, you wouldn't want to check object pointer equatability. You'd actually want to check value. And that depends on if you have unique values or not. So you're going to have to customize this a little bit. All right, so that's our basic setup for delete. The problem is if it's the head node or the tail node, now we're going to have problems where those are going to be pointing to the old nodes. So we've potentially removed them. We're only removing them potentially in the tail case because the head case is actually special. None of this logic, if the node that we want to remove is the head, and let's just look at this. So if we just run through this, so if current is equal to head, and this is one of the things that you want to do is you want to run through the algorithm with some test input so that you can find those edge cases. So if current is equal to head, and then we say, give me the next thing. And let's say in this scenario, we're back to that append situation where we had a single node and we're trying to remove it. We then ask for next. Current.next is nil. And so none of this actually runs. So nothing happens. So we're not deleting. So that's where there's still another edge case that we have to handle. But it's not just for the empty. If we had 2 nodes set up and we tried to remove the head here, what are we going to do? We're going to say current is equal to head. So head is now 4, current is 4. And then we're going to say, give me the next node. The next node is tail, which is 12. Well, in this case, it's just 12. We're just going to 12. And so we get that. And we have our previous is equal to current. So now previous is 4, but 4 is the one we want to remove. And then we check to see if, which one is this? If the next one, so we're checking now 12, is 12 equal to 4? And the answer is no. So it doesn't do anything here. So then we just say current is equal to next. So now current becomes 12. And then we say, okay, give me the next node after that. And so in this case, it's going to be nil. So then it's going to stop. So nothing was removed. So that's not helping there either. So let's go ahead and implement the final part. And that's going to be a check against head. And this is going to be our edge case for deleting head. So to do this, we're just going to say head is equal to the thing that's after head. Now, if head is that situation that we just looked at here, then we are just going to say, okay, head is equal to nil, and that has deleted head. Now head is pointing to nothing. The other thing we have to remember, though, is we're removing something, so that also means that count has to be adjusted. And then our last scenario is what happens if we try and remove something from the tail. So let me just scroll down here. If we wanted to remove 12 from the tail in this situation, I need the pointer before it, which is the 4 pointing to it. And I need to then update tail, because otherwise tail is still pointing to 12. We could clear out, this logic up here is going to clear out the reference to 12. It's going to just get rid of that. But we're going to have a problem because tail is still pointing to 12. And so now we have like a dangling node that's still alive because tail's pointing to it. And if we start appending, we're going to now have 2 lists and it's going to be a problem. So in this scenario, we're going to check, is node the tail? And if so, and that is one of the reasons why we have to have previous in this delete. In a doubly linked list, this is a lot easier. In a single linked list, we need to have some extra state to make this possible without having to run through the whole list again. All right, and so if we go ahead and run this and run our tests, everything should pass. If we look at some of the output, you should see that it's appending, deleting, and you're going to see that the list is growing. And all of the tests have passed. So if we jump on over to the tests, got all of these tests covering a bunch of different edge cases. With some print statements, you can add more if you want to. Generally, I don't keep print statements there, but since it's a code challenge, you won't have the debugger, you won't have these unit tests, you're just going to have prints. It's a good idea to be able to see what's going on. All right, so that is deleting, that is appending. We did it all on one page of notes right here. And thanks for watching. So if this was helpful and you're interested in how to do this with a doubly linked list, I think I'm going to go a little bit faster. But I'm not really sure how fast it's going to go. I'm going to cover how to do a doubly linked list. I think being really comfortable with this, being able to see the shapes, understand the structure is really important. I think very visually, so being able to see my notes over here on the right and then compare that to the code is super helpful. And then just going through the algorithms and understanding them. Understanding how the recursion is sort of working with description, understanding how we're iterating through and keeping track of both a current and a previous node pointer, and then doing bookkeeping at the end to catch those edge cases. And then append, we just had sort of the initial state. We need to set head. Otherwise, every time you're adding, you're just appending to the tail. And then tail is always getting updated. Count is always getting updated. Thanks for watching. Click the like button if this was helpful, and I'll see you in the next video relating to doubly linked lists, or I think I'm going to have an LRU cache solution to a code challenge. It's really hard, but this is one of the fundamentals that you need in order to get that to work, and you need to be able to crank this out quickly. Thanks, and I'll see you in the next video.